Okay, parameterization. I will talk about in a minute about the parameterization, the IDMX parameterization, but I already show you a result of this parameterization. And in terms of the energy transfer from the mean flow to the waves, or the other way around, in an ocean model of the North Atlantic, which has eddies, here this is just a snapshot, and this integrated, or the A times omega dot in this units, you see that there is some energy transfer in red, which means from the mean flow to the waves, right? But there's also blue, and that means the other way around, from the waves to the mean flow. So the waves can either drag the mean flow, that's when it's red mostly, and sometimes there's also the opposite. The waves can drive the mean flow. This is when they propagate into critical layers and break in critical layers and get dissipated. And you might want to ask how important this process is. We can compare it to other dissipation rates in the model, and we have biharmonic friction in the model. If you don't know what that is, doesn't matter. You need it mostly for numerical reasons to make this model stable. We don't like it very much, but this is of course a physical thing, and it's about 10 to 15% of the dissipation which you really need in this model to make it stable. So we are on the way to replace this biharmonic friction with this, but we are not yet there. But we also have this other effect, absorption in critical layers, and this slide is about absorption in critical layers. No, this was the previous slide. No, yeah, this is about this wave drag. We have these relations, and this non-acceleration, there's no effect without dissipation, and one dissipation effect could be critical layers, right? Critical layer is, if you look here at the dispersion relation and solve for this m square, alternative dispersion relation, you see that the m square gets crazy if you shift your frequency by Doppler shift beyond f, or to make it smaller than f, right? Usually this frequency, this is the intrinsic frequency is larger than f, but if you shift it with a Doppler shift towards f, then you get the critical layer where m is getting infinitively, and that means that the wavelength gets very small, energy is distributed over a small wavelength. That means something catastrophically is happening, the wave is breaking, and therefore it's called critical layer, right? Because it's critical that the wave is breaking. And also it stops there, actually, wave propagation, the energy propagation stops there, and yeah. But what happens during the approach towards the critical layer? How's the energy exchange, actually? That you can consider with the wave action equation, because during the way into the critical layer, the ray, or the action of the ray is conserved. And this is the action where you start with your ray somewhere at T0, and this is where the action where you end in the critical layer Tc. And you can solve for this energy in the critical layer. It's a fraction f over omega of the initial energy, and that fraction is smaller than omega. It's smaller than 1 because omega is always smaller than f. It's always larger than f. Sorry, before you hit the critical layer. So, and that means that the fraction is giving to the mean flow. That's this blue stuff in the previous figure. So that's driving the mean flow, and the rest of it must be dissipated and can be used for mixing, given to small-scale turbulence, where there's a forward energy cascade and can mix the density, or you can generate secondary waves, whatever. The mixing aspect is important, which I will talk about later, not only of critical layers, but also of other processes. But there's not much time anymore, so this effect we want to parameterize, but of course also Rossby waves, right? And this is a figure here showing you, again, a model of the North Atlantic mostly, and there are eddies, right? You see meanders and which you call mesoscale eddies in the ocean. Very similar thing as the synoptic scale eddies in the atmosphere, but they are smaller because the Rossby radius is smaller in the ocean. And they are moving on a time scale like weeks to months. They are very slow as the Rossby waves. And you can consider these mesoscale eddies also as a superposition of Rossby waves. So there's not a real difference between eddies and waves in our framework. And of course, instabilities means you're producing mesoscale eddies, but you're also having energy transfer between mean flow and waves. And so we are in the business. We can apply the same concepts also for Rossby waves, which we have talked about before, all this stuff. The difference is, of course, that the starting point can be different, and you start with quasi-geostrophic approximation. Who knows about the quasi-geostrophic approximation for the equations of motions? Some who don't know about the quasi-geostrophic approach. Don't be shy. It's not a, you won't be blamed not to know it. Problem is that I won't explain you what it is, but I can show you the result. The result is that you start with equations of motions, which are complicated. Then you apply your approximation, and one aspect is you get rid of all the gravity waves. You only have Rossby waves in what's left from the equations, and this is what's left from the equation. It's called the quasi-geostrophic potential vorticity equation, and it involves here this psi, and with the psi, that's the stream function for the flow. You can also calculate all the other quantities which you want to know, or the most important quantities which you want to know. Not everything, but most of the stuff. This quasi-geostrophic approximation and potential vorticity and the balance and fast and balance stuff that will also be mentioned by a talk by Manita this week. But here I don't want to talk about in detail about this stuff. I just want to use this potential vorticity equation. And here, vorticity is split up into background and perturbation vorticity. You also have your beta planetary vorticity gradient, which is this term. And there are still some nonlinear terms, epsilons, maybe the Rossby number, smaller than 1, which I keep here for reference. You have to get rid of it for all the stuff which I showed you before. That was all linear, no nonlinear stuff. But I will, of course, we need this sometimes, so I'll keep this here as a placeholder. Then if you make it simple in the first step, then you can do plane wave ansatz and blah, blah, blah. You get your dispersion relation for freely propagating Rossby waves. It's a bit different from what you've seen maybe before here. There's usually the Rossby radius involved here. Here we have an m, which is the vertical wave number, replacing this Rossby radius stuff, because we are now talking about freely propagating Rossby waves, also vertically. Right? So, and then what follows is the same thing. You apply this WKB ansatz, you have your wave frequencies, wave numbers, and you have your small parameter, and you have to do your assumption that mean flow and n are varying slowly compared to wavelength and period of the waves. Sort in orders this equation here, and you get your dispersion relation again, which is the same as from the previous slide for the plane wave ansatz, but now with u and no, basically only u and n here also varying, and therefore also the k varying, and this K1 varying, and the frequencies are varying slowly. So that's the same thing. And the Doppler shift, that's also the new thing compared to the previous one, because we have no mean flow. And yeah, and then you have to go through the exercise for first order. And I just want to sketch this here, what happens here. These are the first order terms. And it's of course tedious to look at. Maybe we can pick here one thing. This is the advection of the background vorticity gradient. You have gradients in psi and then this background vorticity, right? Both will give you an epsilon, right? Which gives you an epsilon square term, right? But but for the psi, you have to differentiate this psi hat, which is a function of x, but also this thing. This thing gives you one order less in epsilon, right? So only this term here with the k, where k is d theta by dx, is the first order term. The next one would be second order. So this term, maybe you understand why this is a first order term. The beta term, which the zero order beta term shows up here in this x dot, the group velocity. But these are all details. It's messy and it's complicated, but it's possible to go through this. We still have this s, and then you take this first order relation. Right? Remember that psi hat is a complex number. So what you can do is you can multiply this equation with a complex conjugate, and you take the complex conjugate of this equation, multiply it with psi hat, and then you add both, then you get a real equation. This term by magic also drops, everything is real. And of course, psi hat square is related to energy. You can rewrite it like this. And then if you're clever, you can come up with relations like this, relating the k's, the omegas, and the m's with each other, all only looking at your theta, right? And if you use these relations, you can simplify to this form then finally. Okay, this is the hard way, right? It takes you days to do this. But, or maybe not you, because you're clever, but me, it took days or whatever. But there's also a clever way by Rines and Young. You just postulate entropy conservation instead of action conservation. Your P is now it's not E over omega, but E times K squared. And then you postulate this conservation equation, then you replace your P with E times K squared, and some numbers, but much less than before, and you end up with your energy equation. Right, so that's then the version, the energy equation, not for gravity waves, but for Rossby waves. And you can also check if the energy exchange terms, these two, are the ones which should end up in the mean flow energy. If you go through the math, then you do the same thing. Here you only need psi, actually, to calculate your eddy stuff. The U and the B can be all calculated from the psi and this ansatz, and to lowest order, you can calculate these eddy fluxes. Turns out that the vertical Reynolds stress is 0. You only have this one here, and the lateral eddy stress, or the lateral eddy stress. And as before, you can now put this into your model as a parameterization if you know the E. And the E you know from the evolution equation in principle from your energy equation for the waves. So then if you calculate the energy exchange, this is here the lateral shear exchange term. This would be the vertical shear exchange term. You compare this with the Rossby wave energy equation, you see it's the same, but with the opposite sign. And different to the gravity wave drag stuff, or the gravity waves, they have no different names. They have the same meaning, exchange by lateral shear or vertical shear. But for lateral shear, you call this the barotropic instability term, and vertical shear, you call this baroclinic, or energy transfer by baroclinic instability. That's the fun thing. You can also show that WB is the same as this effect here, which is important if you look at the Lorentz energy cycle for eddies or Rossby waves. I said in the beginning, waves and eddies can be taken almost the same. So we can look at the energy cycle in this form, Lorentz energy cycle. Who has heard about Lorentz energy cycle before? Can be made both in ocean and atmosphere. Some do, some don't. So it's like you have mean quantities and you have eddy quantities, and you have exchange terms between them. And for the ocean, the cycle is like this, that you, by the wind blowing over the ocean, you generate Ekman transports in the surface ocean, and then you generate divergencies of Ekman transports. You pump water down or up, so you lift isopycnals up and down. And it's stored here then in this mean potential energy. And by slumping or lifting or lowering the isopycnals, the mean isopycnals, you have steepening isopycnals or sloping isopycnals. And their baroclinic instability is kicking in and generates eddies. This would be then this term here. That's what we call the transfer by vertical shear or baroclinic instability. And I think Julian will talk about this in the ED model, right? In the classical ED model, basically this transfer. And this is the most important term or most important mechanism to generate eddies in the ocean, or Rossby waves, by the wind and this baroclinic instability. And then this term here, and this is mostly the same. This would be W times B, this arrow, and this is this in the Rossby wave energy equation. It's the same, and you also see this here in this estimate. I didn't say that. From a realistic eddying or global ocean model, these estimates of these transfer rates and also of the energies, but they are not shown here. So that is the main way here to generate eddies in the ocean by baroclinic instability. The other way, that's the lateral shear term, is apparently of minor importance. It's this way here. So baroclinic instability, you need to parameterize in an ocean model. Janet McWilliams' parameterization would do this for you. You can also do this differently. And with our concept. Before I start to talk about that concept, let us shortly compare what we know now about gravity waves and Rossby waves. So they both, when we don't have lateral shear, at least, we ignore this for a problem, that's a complication. Then we have the same form of the energy equations for both, for gravity waves and for Rossby waves. This omega dot is vertical group velocity times the scalar product. The only difference is the group velocity. Group velocity is much faster for gravity waves, but the other aspects are all the same. The same relation between the sign of M and Z dot, right? Shows up here for Z dot of gravity waves and Rossby waves. the mean flow energy exchange by the vertical term is the same. Actually, the lateral shear term is different because of the entropy conservation different to action conservation. But that's a complication, and this is the more important term anyway. And but they have different names, right? Wave drag for gravity waves and baroclinic instability for Rossby waves. But the process is more or less the same, I think. And compare them in terms of growth rate. If you call this here gamma E, gamma is a growth rate, right? It would be the ED growth rate in the ED model. That's an important concept, right? You might have heard about the ED growth rate, which is almost the same as an eddy growth rate, right? But it's a different name. It's one different character. And it comes here in terms of 1 over days. So the growth period would be then like 20 days for gravity waves. And shorter, the period would be much shorter for gravity waves in the maximum than for Rossby waves. So gravity wave drag would win compared to baroclinic instability in terms of growth rate. But of course, we know that baroclinic instability is much more important than gravity wave drag in the ocean. And I think the reason is, although here the values are smaller, I think the reason is that the energy is concentrated on the small scales, right? Small scales have more energy than the larger scales. Sorry, here the long scales have more energy than the shorter scales, which we have here for the gravity wave drag. So in the long run, baroclinic instability still wins. Okay, and now for the parameterization. There's one step missing before we can put what we know now for parameterizations in the ocean model. We have to transfer the wave action, which we had previously per volume, also to wave number space in this way, because we don't consider not only one wave package, one ray, but an ensemble of rays, of course. There's not just one Rossby wave in the ocean or one gravity wave, but a spectrum of waves. And therefore, you have your action density or entropy or energy density or whatever, not only per space, but also per wave number space. So not only x and z, but also k and m. And that has a consequence for the conservation equation, which I want to detail now. You still have, or you still say that in this space, in this six dimensions, right? 6-dimensional space, there's still action conservation of your parcels flying in this 6-dimensional space. So a parcel here starting with this action and this volume of your space is the same as the action in a little bit later, the time delta t later. And the change in x is then delta t times x dot and so on, times the deformed volume in your space, the new volume which is covered by your parcel or whatever you have, ray or wave package. And but what you have is volume conservation in this space. It's actually handy because then frequency becomes a stream function. We have this relation here. This is the volume conservation or the volume divergence, if you want, in this 6-dimensional space. The first two terms are volume conservation in the physical space. The other two are the corresponding ones in wave number space. And just by using definition of your x dot and so on, you see they all vanish, or the sum is vanishing. Or you say that omega is a stream function for the flow in the 6-dimensional space, right? But because there's volume conservation, this volume here must be the same as this volume, right? So you can equate them. And then the last step is to do a little Taylor expansion of this thing here. And it gives you then expansion like this, and it gives you the radiative transfer equation or action conservation equation in parcel form, or in the 6-dimensional form. Interpreted here as parcel form, or if you then go back to flux form, looks like this, right? And there are other names for this, called sometimes Boltzmann transport equation or energy transport equation. We call it radiative transfer equation. You can formulate this for gravity waves, for Rossby waves, for electromagnetic waves, whatever, or for surface gravity waves, always look similar. Maybe you have to exchange wave action with entropy if you switch from gravity wave to Rossby wave. And maybe there's not a zero on the right-hand side, but something which is left out, which is forcing dissipation, other nonlinear effects. Okay, and this equation is, and the difference to before is we don't only have this, not only have this propagation in physical space, but also in wave number space. But the terms are analogous, right? It's a propagation speed in k, and you take the divergence in k direction, and the same for m direction, right? Same thing. So you can think about, use this as a energy, or you can then formulate the energy equation and use this as the equation which tells you the energy of your waves per wave number and for physical space. Well, here's the energy density equation for gravity waves with these two terms. They're the same as before on the right-hand side, your omega dot times A, and here we have the corresponding version for the Rossby wave energy. This is then the baroclinic instability term. This would be the gravity wave jet term. And the idea is now to use this energy equation and to integrate it, right? And there are two different flavors. Now, one flavor is use this gravity wave equation and write a model in 6 dimensions plus time and integrate this in time and try to understand now or use it to try to understand the interaction between the waves and the mean flow, because this is what it describes here on the right-hand side. Right, that's we call IVAM, and Pablo sitting over there, he will talk about this, how to understand with this model wave mean flow interaction. And another application would be actually a surface wave prediction model, a wave model, which is coupled to an ocean and atmosphere model sometimes. And they would have the same version here for surface gravity waves, and they also integrate this in time and predict the surface, the wave state, the sea state in using weather prediction forecast models and so on. But we do this for internal gravity waves, IWAM. And the other route is to couple this to an ocean circulation model to predict your eddy flux, your eddy fluxes, and to put the eddy fluxes in your model, right? But the problem is, of course, this is too large. If you have 6 dimensions, your model has only 3 dimensions, you don't make the model faster, you make it slower, much slower, right? So the idea is to make, to use this, but to apply a reduction in the dimensions, but still to use the same equation to predict the effect of waves on the mean flow and use this as model parameterization, which is then energetically consistent because we have shown that this is the same energy exchange with the mean flow and the waves. So I won't talk about this first, but about the latter, the ID mix concept. That's what we call ID mix. The name comes from this first version called internal wave dissipation, energy and mixing. Why this name was chosen, I will show you in a minute. The idea is to take this equation but reduce dimensions, and we reduce in k dimension, in wave number space, k and m actually. But we keep the physical space. And the trick to do this is to assume that the actual energy density is close to something like this, a factor E0, which is spatially dependent, and which is then the integral over the energy density at this point, times a shape function, which is normalized like this, and which is taken close to the observations actually of the wave field in the ocean. In the beginning, I showed you that the observations have these slopes, right? We have the famous Garrett and Wang spectrum. So we assume that the B is the Garrett-Wang spectrum. Then we can be sure that the actual density is always close to, or this thing is always close to the actual spectral density. That comes from the observations, an empirical law. And then you integrate your equations, maybe this one here, over K and M, the flux Z dot times epsilon, or the energy density. And you can write it like this with a C, like this from this definition. If you use for this energy density, this expression, then you have Z dot times B, and both is known. Z dot from the polarization or from the dispersion relation, and B from your assumed spectral shape. So you can calculate your C. That's like a mean vertical group velocity, which you have then after integrating this equation. And then you go on and do this for the other terms, and you're basically done. Right? That is the idea. Problem is the S term, which I will talk about in a minute. And of course, there are many other complications. What happens if this is not so close? What happens if WKB approximation breaks down? What happens if whatever? But, and we also have a zoo of these parameterizations now, which is also a problem. But it came along because we focused first on one aspect and then on the next aspect and so on. We started out with this simple ID mix for a vertical mixing parameterization, and that one I want to show you in more detail on the next slide. And we extended this slightly, and we also looked at Rossby waves, of course, to parameterize baroclinic instability, and also the gravity wave drag. In this first version, we ignored this gravity wave drag, but then people told us this is also important. So we wanted to have it. And of course, then you also can do this for the atmosphere. And in this paper, we have now an atmospheric gravity wave drag parameterization, which of course outperforms all the other parameterizations in the world. Oh, this is just a joke. Lee waves are also important in the ocean. Lee waves are generated by flow over topography, right, in the atmosphere, but you also have it in the ocean. It's an important driving mechanism. And then you can also make it more complicated with not just energy, but also some other aspects of your spectrum, of your spectral shape in the B. You can make it more complicated. But you can also make it more simple, maybe. So we are still working on this, and we are extending the list, of course. But firstly, the vertical mixing, that was the start. And that actually not only deals with this advection, we skipped this part, but mainly the S term, actually. And that's the complication. That's the S is forcing and dissipation, but also the nonlinear interaction between the different waves. And that's, of course, the hard stuff. But we thought that we got a clever parameterization for that to handle this. So to understand the S term, you start again with your Navier-Stokes equation, like non-hydrostatic Navier-Stokes with some Boussinesq approximation. That's not so important. What's important is that you have these nonlinear terms here on the right-hand side with an epsilon in front again, which is the Rossby number or some other small parameter. And what you can do is you can do a Fourier transform with a spectrum of waves or wave amplitudes. That would be then this A here. And if you only consider the linear system, you can solve for the waves. And the waves are comes actually as eigenvalues of a matrix, of a system matrix, of the linear system. And one eigenvalue is the one for the Rossby waves, and there are two others for the gravity waves. So these are the wave modes then in the linear system, one Rossby wave and two gravity waves. And you can also do this for the nonlinear system, but of course you have problems here with the nonlinear terms. They give you these double integrals, right? The convolution integrals of involving amplitudes of two different waves. And also, and A1 and 2 means here the different wave numbers K1 and K2, which you need to have in your convolution integral. But also S1 and S2, which are either 0 or plus minus, indicating Rossby wave or gravity waves. So you also have mixed interactions between Rossby and gravity waves. So it's a complicated thing. And of course, your wave ansatz for the Fouriers, where you have a Fourier transform, where you have the frequencies of the different waves at different wave numbers for different Rossby or gravity waves. And this delta function you can use to reduce to get rid of one of the integrals, if you want, one of the three-dimensional integrals. So this is a six-dimensional integral. You can reduce it to a three-dimensional integral, but it's still complicated, right? And there's no approximation. It's the same thing as this equation, but a little bit more complicated, written in a more complicated way, right? And there are interaction coefficients which come from the equations, right? And yeah, this is how it looks like, ugly. But there's the idea from Hasselmann, and that's already quite old. And he did this for general waves, for geophysical waves, for surface waves, for all kinds of waves. And what his idea was to assume, again, slowly changing A amplitudes. So using the fact that this parameter is small. So he called it, I think, weak interaction between the waves, weak interaction theory. And then with some clever things, expanding your amplitudes into the epsilon and crunching a lot of numbers, pages and pages and pages, you can come up with this equation here. Note that this is a complex, for the complex amplitude, this is real again for the energies of the waves. Epsilon is the energy. And here you still have this network of interactions here, but the coefficients are slightly different. And from these product of the amplitudes, you get products of the energies. right? We already resolved one of the integrals here with the delta function, which gives you triads, right? There's always this network between triads. K2, K1, and K are related like this. And you also have the same here in terms of the frequencies in this time response function, right? This is, except for the expansion in the small parameter epsilon, was no approximation made. But if you then say, okay, the time response function, I'm only interested in the long run, right? Then you can show that this expression here goes to the delta function, the real part of the expression, actually. So taking real part here on the right-hand side, you see that you have also the same network between the frequencies in the long run, where only the delta function is then possible. And that's called the resonant triad interactions, right? If you meet with your wave numbers like this, and as a consequence, we have frequencies. If you also meet this condition, then you have resonant interactions, and they are supposed to be the important ones in the long run, taking the real part. The other part gives you this Chouksey integrals. We don't want to talk about this. I think Pablo will talk about this. Right? No, okay. Complications, they're all complications. But in principle, you can write this down, right? This is the idea. And then you can extend this here on the left-hand side with our propagation speeds in wave number. So you're combining both ideas from Hasselmann and this WKB tracing, and put this on the right-hand side, the scattering, this is called scattering integral, because Hasselmann made a connection between particles and waves, and scattering of particles and waves and Feynman diagrams. There are many nice papers from Hasselmann which you can read if you're interested. But nobody is reading these old papers, of course. But we have the scattering integral, and the idea is to use this as a representation for the S here in this integral. So this is replaced then by scattering. But of course you cannot do, because you cannot calculate this in an ocean model. You don't want to calculate this fancy scattering integral. You can do, actually, Pablo will show you some examples where we calculated this numerical for one time, but you cannot do this for each time step in the model, of course. So we want to have a parameterization for that. And to start, parameterization, which we can use in the parameterization. That's now getting a little bit abstract and complicated, but to do so, you have to validate your parameterization. And we started out with a model, numerical model, where a non-hydrostatic model with which we initialized with what we see in the ocean, this GM spectrum, right? We put the GM spectrum in a block of an ocean model with these dimensions. This is vertical space, this is horizontal, with periodic or triple periodic boundary conditions. This is the spectrum. This is how the GM spectrum looks like in K and M here. The horizontal lines are different frequencies. This is 2F, 3F, and so on. And yeah, and this is how it looks like in physical space. It's little wiggles, right? These are the internal gravity waves and the spectrum of these waves. The color is the U velocity, where you mostly see the large scales. So this is the model and realizations of that in its ensemble simulation. And we can compare, and we can calculate the d by dt of the spectrum in the model, the change, which is a bit complicated because you have a damping in the model, which you have to reduce, or if you have to subtract from this d by dt. But if you do this with tricks, then you get this change of the spectrum. It's changing between, well, it's getting reduced by between 2F and 3F here for many different wave numbers. And it's getting more here, right? So that's what the numerical model says. Then we can compare it with the scattering integral, and you hardly see any difference, right? I can almost not tell which one is which. So that's Hasselmann's scattering integral, or the prediction from Hasselmann's scattering integral, showing you that it does a reasonably good job, right? You compare both. With Hasselmann's integral, you can also go a little bit beyond the numerical integral here. Of course, the numerical integral has delta x, delta y. You cannot cover all the range here, but with the scattering integral, at least with the resonant interactions, you can cover more. You see how this extends. And more of this will be talked about by Pablo. And if you integrate here in kh and only plot it as a function of m, here you see this. It takes away energy at the small m, put it at large m for two different versions of this GM spectrum. There are different versions, slightly different. But it's like a forward energy cascade, right? It's in flux towards higher wave numbers, where the energy is then concentrated on smaller wavelengths, larger m, where the waves are then supposed to break. So that's like a forward energy cascades towards dissipation. That's the effect of the scattering by the wave, or the wave-wave interaction. The nonlinear wave-wave interaction generates a forward energy cascades towards small scales where the waves break and dissolve into small scale turbulence. So that's nice, but we need to parameterize this in the IDMX model because we don't want to calculate the scattering integral. So what we have is this form, and this is not our idea, this parameterization, that's called the fine structure parameterization. It's a way to estimate the dissipation rates by internal gravity wave breaking in the ocean, actually, from observations, from casts, from Argo floats or CTD casts or ADCP casts. You can use this. And that's the same formula as what we use here. A parameter times total energy, and E is here now the energy integrated over your frequency in M or wave number space, squared times a parameter mu, which we call mu here, which depends on F, on C star, and on the slope of the wave spectrum, which we prescribe. Doesn't need to be always -2, could also be -0.1 or 0.2, 1.2, 1.1, or a little bit less, or whatever. And we check the calculation of the scattering integral in terms of the removal here in this blue band and the energy transferred to the high wave numbers as modeled here with this parameterization and with the scattering integral. And the dots are the scattering integral, the lines are the parameterization, and it fits almost perfectly, right? And this dependency on F and the bandwidth is very close to what they have in the fine structure parameterization. The S dependency they don't have yet, but they could also implement it and improve the fine structure parameterization. So we are quite proud that we have this parameterization now, and this can be used now to parameterize the S in the IDMX model. And this is then shown here. We start with this energy transfer equation. You reduce it by integration over wave number and also this assumption of the spectral shape. But there's this S term, which we want to keep. We throw away the gravity wave drag for the moment. That was a different paper, different task. And so no U, basically. And also we say that there's no lateral homogeneity, inhomogeneity. So in X and Y, everything is the same. Then we can forget about this term and that term, right? And we integrate over M and K, all the terms. You see that this term integrates to the boundary values, which we set to 0. We only have the integral over that term, but I already showed you what happens to that term. We have the C with this by group velocity to handle that term. The difference to this slide before is, of course, the integral over S, and that I'm integrating not over the full spectrum, but I'm dividing it into two compartments. One where the integral is only taking about the negative m's, and one for the positive m's. The negative m's, they correspond to upward energy propagation. The positive ones, they correspond to the downward energy propagation. Upward going rays, downward going rays, right? You split this up into E plus, E minus. Then it comes like this, right? And also the integral is only about plus or minus m. And but the C is the same for both. And of course, the equation is also highly reduced, right? From 6 dimensions here to a vertical integral or the vertical differential equation. But of course, there's this S term, and to see how to get parameterization for that, we write it for the sum and the difference, like this. Then you have here this total integral over S, and here the integral of S term for the upward and downward propagating waves. And now the closure is, for this total S effect, we can take the mu epsilon square. Right, because that we shown before from the scattering integral that this is a fine structure parameterization, that this is a clever parameterization for this term, For the other term, we think a clever parametrization is that the effect of S on the difference between upward and downward propagating waves is to damp it. The linear damping scale is introduced for this effect of the nonlinear interactions between the upward and downward propagating waves. They damp the difference between up and downward propagating waves, and to make it isotropic in terms of up and downward propagation, because this is also observed that there's not much difference between positive and negative M in the wave field. In the GM wave field, there's no difference. It's the same. In observations, there is sometimes a difference, but we think that the reason is that in nonlinear interactions, they damp this interaction. Okay, and then we are closed, right? Then you have a simple model which you then can co-integrate in your ocean model and predict the epsilon. And with the epsilon, you can, in principle, predict other stuff. But here, actually, the focus was on the S term. So you can take then this dissipated energy by the wave interaction and put it and use it to calculate the mixing rates in the model. Right? There's another step. You put this energy to a small-scale turbulence closure or into the Osborne-Cox relation, where you can calculate your mixing coefficient from. Who knows about the Osborne-Cox relation? Nobody. Yeah, don't worry. It's an intermediate step to get your mixing rates from these energies. Energetically consistent, of course. Whatever, and that's the simple parameterization. This is this simple ID mix version, and it can predict then the mixing rates, the density mixing rates in this ocean model, which is an important thing in an ocean model. Not so much in the atmosphere, but in the ocean it's a big thing. And this is a comparison here between mixing rates from Argo, or dissipation rates actually. This is the actual dissipation. Argo floats are global observation system where you get profiles from time to time, from day to day, from which Friederike Pollmann calculated dissipation rates. You see here, these units, there are differences in the global map, and this is ID mix, and you see that there's a correspondence between both the parameterization and the actual dissipation rates estimated in the ocean. And from that, you get the mixing rates in the model. But of course, there are issues, there are large errors in the observational estimates, and of course also errors in the ID mix model. This already showed, that's the second example, the gravity wave drag, that's this other version, which we think is not unimportant in the ocean. Of course, more important in the atmosphere. There's this atmosphere paper, which I don't show you. This is a figure showing the instability, baroclinic instability, using the same concept for Rossby waves. I don't go through the details, just show you here idealized simulation of a jet. Here this is Y, this is Z. Here you have a jet which has positive velocities here, negative velocities here, sloping isopycnals and geostrophic balance. This is Y and this is time here at one depth, 200 meters around here. You see here the jet in an ensemble of models which gets unstable. This is baroclinic instability. Eddies are formed and something is happening. This is this baroclinic instability which you want to parameterize in an ocean model. This is one ensemble member. This is the ensemble mean. You see there's something happening, right? So it's not so easy to see. And this is then the parameterization. The onset of the instability is different in the actual model and the parameterization, but then what's happening later is very close. There's this blue stuff in the middle, and then there's reverse flow of the central jet, which we reproduce, which is introduced by the eddy stresses, which we also have in the parameterization. You see here, without eddy stress in the new closure, you don't see the red parts. And this is the Gentleman-McWilliams parameterization, which is much simpler than our version, of course. It doesn't have this recirculation, but it also looks very good. That's actually the problem in ocean models to parameterize baroclinic instability. Gentleman-McWilliams is not winning, but it's very hard to compete, actually. Anyway, but we think we are still better than Gentleman-McWilliams. Okay, this is the end of my talk. I showed you how to construct these energetically consistent model parameterizations for interactions of different dynamic regimes here, based on this radiative transfer equation and the knowledge about waves which we have. And this is the work which we do here in this CSC 181, which Manita mentioned. There's also a web page which you might want to visit. And yeah, thanks very much for your attention. Oh, sorry, I didn't mention that this is IDFIX, right? And Dirk chose the name, actually, it's not my name. IDFIX, that's the German name for this little dog in this comic strip from Obelix and Asterix. I don't know if you know it, maybe you know it. And the name is similar. So this dog, this pet pops up here.
Yeah, we can have some questions. Maybe I'll start. So you spoke a lot about the wave packets, wave mean flow interactions, and then you jumped into nonlinear wave-wave interactions. So in this parametrization, does that come in wave mean flow interactions, and how do they compare with the nonlinear wave-wave interactions?
Yeah, it's all in this S term, right? On the right-hand side. In all this WKB theory, you don't talk about nonlinear action. You set the nonlinear terms explicitly to 0. But they are there, right? And for density mixing, they are important. For gravity wave drag, you can forget about the S term, and you only focus on that. In the atmosphere, you wouldn't talk about this S term for the atmosphere parameterization. But for the ocean density mixing, that's important, this term. And so you have to go through the nonlinear wave-wave interaction, or wave-wave interaction, which is nonlinear, and the scattering integral and all that to get a parameterization for the S. Parameterization in the parameterization, so to say. That's the idea. And of course, this is not the end of the story to understand the scattering integral. Pablo will talk about this more. And there's also the problem of interaction of the Rossby waves and the gravity waves in the scattering integral, of course. Whether there is a resonant interaction or not, but there is no resonant interaction, but there might be interactions. That's a long story.
Use the microphone.
So were you reading out the question in the chat?
No, you go first.
I'll go first? Okay. Just a very quick question, but so from what I know of gravity waves, the context in which I first encountered them was geostrophic adjustment. So if I have a mean flow or a leading order flow that is in geostrophic balance, and if I apply the quasi-geostrophic equations to see it evolve, I constrain it such that the final state is also in geostrophic balance. But in reality, it might spontaneously be emitting gravity waves for that assumption to hold. So does that require, I just wanted to know, is that represented as a forcing? Like, is that represented as an additional source term, or does that show up, is that covered by this wave action that you've talked about?
That is a good question, actually. That touches what Manita will talk about, if there's actually a connection between this Rossby wave stuff and the gravity wave stuff. If you say that you have a flow in geostrophic balance, which evolves somehow, and radiating gravity waves, that's geostrophic adjustment, right? Then you could say that in the beginning, your flow was not in balance, right? You can balance your flow, and then it won't radiate gravity waves. And then you have part of the flow, which is almost given by the quasi-geostrophic approximation, which is completely separated from your waves, right? It evolves independently of the gravity waves.
Presumably, it would continue to radiate gravity waves from time to time, because
so, yeah, that's the question.
A geostrophically balanced solution, if I'm not wrong, in the primitive equations doesn't stay geostrophically balanced.
Yeah.
So it would...
you refine your geostrophic balance to a nonlinear geostrophic balance, and then it might stay balanced. That's the balance. That's the issue of flow decomposition, if this is possible. Might be that all balanced states, they might generate gravity waves all the time. That's called spontaneous loss of balance, right? But we think that's very, very weak and almost indetectable. But there are issues with this, and Manita will talk about this in detail. It's this issue of separating the flow, the complete flow, into a slow manifold and a fast manifold. The fast manifold would be the fast gravity waves, which oscillate very fast, and the slow would be the Rossby waves, which are slowly evolving in the nonlinear setting. And the question is how they interact with each other, or if they interact and transfer energy from one to the other. That's an important question, because some people say that this spontaneous loss of balance of the balanced flow, is an important term to dissipate your eddy energy. And that's the problem which we are facing and which we cannot answer yet, but Manita will answer it, hopefully.
It says, are there any materials for learning all these derivations? It's on the screen, the big screen here.
Where do we learn all these derivations? Carsten, that's the question.
You have to go to your lectures, right?
Oh, yeah. Where to learn? This is a good question. Of course, there are books. You can read books, right? But it's not all in the books. It's partly in the papers, which I mentioned, and partly in textbooks. So it's a bit scattered, all this theory. And the good news is that Dirk Olbers, he is writing a book about internal gravity waves. Only internal gravity waves, but the Rossby wave stuff is very similar. But it's not yet ready yet. It's that thick and it's heavy and it's not easy to read. But there will be a book about this, and maybe this year or next year. And that you can read. Or I can pass you the slides, the PDF of the slides, and you can also check it out.
Any more questions? All right, if not, we'll thank Carsten again. Thanks, Carsten.